All, all right, you guys. So we are on lesson 2, starting with chapter 3, physical and mechanical properties of dental materials. So there's a lot of information in here, so we'll just jump right into that. Today we're going to be talking about the 3 different categories of properties of dental materials, and then delving into especially physical and mechanical. So the 3 different types are in bold here. You have physical, chemical, and biologic. Mechanical is a big part, but it's actually a subgroup of physical properties. So let's look at that first. Physical properties are pretty easy to remember based on the laws of physics. So it's even part of the word there to make it easy to remember. It doesn't involve changes with composition or primary bonds. And it's used to describe things such as mass, energy, force, light, heat, electricity, etc. So think of, when you think of physical traits, things such as color, density, how well it conducts temperature. An example of this would be galvanic shock. So if you were me and ever a kid, and I don't know why we did this, but if you had any amalgam fillings and then you took a piece of a gum wrapper that had an aluminum coating and you'd scrape it across your fillings while you were biting, it would create an electrical shock. So that's one example of a physical property. Then when we look at mechanical, that's how strong a material is. How well can it resist forces? And that would be its strength, stiffness. For example, metal is going to be stronger usually than a composite. This really depends though on the amount of material. So for instance, an amalgam, the atomic bonds, there are more atoms present in that material versus a composite. The size of the object. Sometimes certain materials that are bigger are not always stronger. For instance, if you had a full composite overlay, that's not going to be as strong as a full zirconia crown, right? And then the shape of the object as well. That kind of coincides with that overlay compared to crown analogy I just mentioned too. And then we have our chemical properties. So this is how things are changing chemically. This helps us describe the setting reaction or degradation of materials. For instance, we polymerize composites by using a curing light, helps set them. Over time, amalgam can actually corrode, and you can see some of the corrosion around the edges that are a little bit dark right there, and everything. And then we have our biologic properties. So this helps us understand how a material is going to affect living tissue, mucosa, tooth structure, everything in between. So a good way to remember this, I think of the biological width rule, and this gives an example of this tooth had a restoration of the margin that was very, very close to the alveolar bone, is in that yellow dotted line. If you don't know, the biological width rule talks about how the bone needs to be at least a little over 2 millimeters away from a material. Otherwise, the alveolar bone is going to get destroyed and try to get away from that irritant. So you can see here, this is the before, that the tissue is obviously very, very inflamed, enlarged, puffy. And when that material is reconstructed and appropriately sized, it looks so much better, right? This is the after. So that's one little way to understand what are the biological effects of a material. And then we also have, I put a picture here of an example of an allergic reaction. So this patient had a temporary crown placed, and this was 12 hours later of a pretty severe allergic reaction. So different things can happen with different materials and different sensitivities to the patients too. All right, and then moving on to what are some specifics of physical properties. So big long list here. We have things that we'll break down here: density, boiling melting points, vapor pressure, thermal conductivity, heat capacity, heat of fusion, vaporization, coefficient of thermal expansion, and electrical conductivity, and the list does go on. Viscosity, hardness, durometer measurements, abrasion resistance, solubility, water absorption, color, and how things interact with radiographs. So let's start with density. Usually when you think of, that's how much something might weigh. So the material is measuring its mass per given volume. So mass is its resistance to being moved, and volume is how much space it's going to take up. And this really depends on the type of atoms that are present. So higher number of atoms, you're going to have a higher density. So think of your amalgam as pretty heavy compared to a composite, right? Because there's more atoms closer together in metal, which goes to the packing of the atoms. There's a little bit more space in between composite atoms. And then, of course, if there are voids in your material, definitely that's going to affect the density. So just think of metal's more dense, weighs more. It's going to take up more space in those atoms. And then we have boiling and melting points. So what's the difference there? First of all, when we boil or melt something, we're breaking those atomic bonds by using thermal energy. Temperature range versus specific temperature. For instance, specific temperature water boils at 100 degrees Celsius, right? Whereas something like dental waxes, those have a temperature range. It's not a specific number to where they would melt. So hopefully that makes sense of those differences. Vapor pressure. So this is measuring a liquid's tendency to become a gas, and it coincides with temperature. So higher temperature, your vapor pressure is going to increase. Same thing at boiling water. We know that as the temperature goes up, so does that ability for it to become a gas. And then we have thermal conductivity. And I really like this image. This is showing a candlestick and someone's holding a metal rod. And when you think about in the summertime, in the wintertime, if you touch a metal bar, it's going to feel really cold, right? If it's outside. If it's during the winter, it's going to feel more warm because metal really conducts heat very, very well. So it has a high thermal conductivity. This is measured as heat flow over time, and it depends on different things. How far does that heat need to travel in the material? When you think about metal, those atoms are closer together, right? So it's going to conduct that heat easier than maybe something like composite that has a little bit more space in between those atoms. The area in which the heat needs to travel, and then the temperature difference between the source of the heat and the destination. So, for instance, this doesn't have very far to travel. If your patient has a really deep cavity prep, decay is actually, believe it or not, an insulator. So once that decay is removed and that prep is close to the pulp, that a lot of times those fillings post-operatively can be sensitive because there's not much space between the filling and near the pulp. And pulp is a really good heat conductor. Other things will transmit heat well, again, amalgam, cast gold, or alloys. Things that transmit heat poorly, which would have a low thermal conductivity, are going to be things such as enamel, cements, porcelain, ceramics. And to be a good insulator, a material has to be 0.5 millimeters thick. Also, acrylic dentures, those actually will have a lower thermal conductivity too, so it'll kind of protect the mucosa. And then we have heat capacity. So this measures the amount of thermal energy a material can store. So again, think about our amalgams. Those can store a lot of heat energy, right? The specific heat capacity is the energy required to raise the temperature of 1 unit of mass of material by 1 degrees Celsius. So again, our amalgam is going to have a pretty high specific heat capacity, right? Then we have heat of fusion and vaporization. So what are those? Heat of fusion is the amount of material required to melt a material. So think of heat of fusion, think of a tuna melt sandwich. It doesn't take very much to melt that cheese on the tuna, does it? A partial denture or a full denture are pretty easy to melt compared to a amalgam buildup, right? Heat of vaporization is looking at how much energy is it going to take to boil something. Both of these are going to take a lot of energy to accomplish for dental materials, most of them. And then we're going to look at the coefficient of thermal expansion. So this is a change in volume or length that's shown in a percentage or a fraction in relation to temperature change, okay? So when things are cold, they tend to condense, contract. When things are warm, they expand. So this example is in your text. We're going to see it in a little bit again in a different slide as well. But when you look at material 1 here, it's the same type of material. Let's say it's composite, okay, just randomly picking. The length of this material is longer here. Let's say it's 10 millimeters. And let's just label this one as 5. It still takes the same amount to change the volume as it does when it's this length and this length. And then let's say material 2 is impression material. You know, that same length, it's going to change much more with that amount of heat, right? So let's say if you put a lot of hot coffee and a person's drinking and they have a class 1 composite, that expansion is going to be pretty minimal, right? But let's say you have impression material and you're going to pour that hot coffee on that impression material. It's going to change its expansion by much more. And then we're going to get into talking about, still continuing with the coefficient of thermal expansion. percolation. So this is how things will open and close with the gap between the tooth structure and the restoration due to temperature. And this a lot of times can not result in things that are very good, such as microleakage, where bacteria and things are able to get in between a restoration and the actual tooth. It can create a lot of sensitivity. For instance, here, this is an example of our dentinal tubules that are very porous and open to temperature sensitivity. And then also recurrent decay can happen if you have microleakage or a gap in between a restoration and a tooth, right? Old filling material used to shrink and expand more than natural tooth structure back in the day, but these days materials are much stronger. And so this is less of a concern for a lot of our newer materials that we use these days. All right, and then we're going to talk about electrical conductivity. So there are things that conduct electrical sensations well or poor. So good ones are going to be our metals, right? Because the electrons transmit pretty easily. So don't forget about our galvanic shock. Things that aren't going to conduct electricity very well are insulators, our polymers, our ceramics, things like your composites could be technically semiconductors because they transmit electrons sometimes. And then we're going to talk about viscosity. So that's generally the ability of a material to flow. You can also think of it as how thick something is, how strong its resistance to flow is. So think of maple syrup as really viscous, right? Water has very low viscosity. This also really depends on temperature. That can change the chemical structure of a material, making it more viscous or less viscous. And this also translates to our high and low contact angles and wetting. So wetting is measured by the contact angle of a liquid on a solid. So this next slide, this example is in your book as well. A high contact angle has poor wetting because it's covering, it kind of balls up. It doesn't cover as much surface material. So think of something, again, your amalgam is going to have a pretty low, a very high viscosity because it's not going to spread out versus something else such as gypsum that we will use to pour up impressions to make study models. It flows really well into an impression and covers a lot of surface area. So it's low to that surface, has good wetting, but it has low viscosity because it flows really well. And then, sorry, my dog is here, and sometimes I think he had to swallow. Okay, so hardness is scientifically measured by instruments that press a tip, which is either steel or diamond, into the surface of the material just to see how big of an indentation it leaves. So how well can it kind of resist that? This image is showing two different types of measurements, the Brinell and Knoop. So here you can see this is the cross section of the tips, and then the blue area is the material that it's testing and going into, and then C is the shape of the indentation that it would leave, or the amount of area that it would leave. And Noop has a good visual range here of different materials. So enamel's 350, it's the hardest mineralized tissue in our body. Whereas you can see dentin, our insulator, is pretty low. It's only 70. Porcelain's much higher than enamel. And then acrylic denture teeth are actually pretty soft. And then let's talk about durometer measurements. This is used to determine the hardness of softer dental materials. So your impression materials, things such as ortho rubber bands, the rubber grips that are made for putting on instruments. So it's measuring things that are much softer. And then we have abrasion resistance, or also known as wear resistance. So obviously harder materials are going to be more resistant to abrasion, right? So our metals. Restorative materials that are too hard will wear away opposing teeth. So this image is a good example. Granted, we can't see the maxilla, so it's hard to say, but generally if a patient has, let's say they have porcelain crowns from 6 to 11, and if they have natural teeth on the lower here, the porcelain, remember, is harder than enamel, so it'll generally wear away enamel and cause a lot of attrition. If restorative materials are too soft, it will start to wear away. Certain sealant materials can be less resistant to occlusal forces, so over time they can start to wear down. This poor patient has really worn through these crowns here. And then there's the Goldilocks principle. You want something that's just right. It's not going to be too hard to cause trauma to opposing teeth, but you don't want it to be too soft that the material itself wears away. And then we have solubility. So this is the amount of material that will dissolve in liquid. If you have excessive solubility, this leads to loss of material and recurrent decay. So for instance, sugar dissolves really well in water, right? But oil does not. It separates. Enamel does not dissolve in saliva, thankfully. Solubility is tested by immersing the material in water, and the weight of the material dissolved is its solubility. This image here shows, here's a PFM crown here, PFM crown here. This looks like it's probably an MO amalgam to me, but you can see there's recurrent decay, very, very large, with also a periapical infection. Generally metal, it's not going to dissolve. Porcelain's pretty strong, but things that might be more apt to dissolve over time would be your possibly composite sealants, things that are just a lot less resistant to that. But for instructional purposes, this is just an example of recurrent decay. That's mostly the tooth structure underneath that crown, but it's possible maybe some type of the cement that was used could have been exposed or prone to causing some recurrent decay. And then we have water absorption. So this is something that absorbs water. It's not dissolving, it's actually absorbing water. So an example, when you dunk a cookie in milk, it expands and absorbs that milk, right? Some materials absorb water and dissolve at the same time. For instance, polymers absorb a small amount of water. So these would be things such as dentures, composites, and sealants. They absorb a little bit of water compared to amalgam. is not going to be on that same level. Next here we'll talk about color. This goes along with shade matching with your composites. And I remember from my dental materials instructor years ago, she had mentioned that quite a while ago, women, usually assistants, in their early 20s were believed to be best at shade matching because of their vision. So it's really interesting. But light essentially is what is causing a response to that physical stimulus. And it varies between individuals. So again, going back, for whatever reason, back in the day, it was believed those early 20s women were the best at shade matching. But we have shade guides now that help us kind of standardize so you can know exactly what color composite it's going to have. Just to touch back on light, that's a physical stimulus that reaches the rods and the cones of our eyes. And it distinguishes 3 different parameters. The dominant wavelength, which is the color, so maybe it has a blue hue or a green hue or yellow, orange, red. It also distinguishes luminescence, so lightness of color from black to white, and the saturation of light. The doctor that I personally work with, when he has to do an anterior crown, he does a custom shade match out near almost to outside the office in natural light with the lab, because certain fluorescent lighting can definitely affect your interpretation of a shade. And sometimes too, I know the book had mentioned you can use a digital camera to shade match as well. But keep in mind that teeth have a polychromatic trait. So what that means is that it looks different at the incisal third compared to the gingival third, right? Our gingival third is going to be more opaque, and then it's going to be more translucent near the incisal edge. Light's going to be reflecting off of the shade as well. That can affect what shade you're going to pick. So different things to just keep in mind, especially when you're working on a specific area of the tooth, particularly anteriors. Okay, and then of course we know different materials are going to show up differently on our radiographs. More lucent things are going to be our ceramics. Here you can see those composites. You can tell that there's been a restoration here, but it's more faint, right? Compared to this looks like a 4-unit bridge, PFM bridge. We have our metal and then our porcelain over it. And this poor patient has 2 periapical infections. And then also, of course, again, another PFM crown. It's going to be, any metal is going to show up pretty stark white and more subtle on our composites and resins. All right, next thing, we're going to talk about mechanical properties. So remember, our mechanical properties are how strong a material is. Your metal materials are pretty strong. Porcelain's pretty strong, so is zirconia. You guys aren't going to be working with that, but a lot of times nowadays I'm seeing more zirconia crowns placed in posterior molars because it resists biting forces. But we're going to get a little bit into the physics of elasticity, strain, stress, the relationship between those two, again with a plot as well, what types of stress there are, and then other mechanical properties as well. The Poisson ratio, resilience and toughness, fracture toughness and fatigue, and then also time-dependent properties. So material properties are going to include force and stress. So force is going to be something, that weight that's applied to an object. I really liked this image because you have your finger pressing against a brick wall. You're applying force, but really so is the brick wall, and it's much, much stronger than your finger, right? Stress is going to be the force divided by the area by which it's applied. So the force on your finger divided by whatever this area of the brick wall is. We have elasticity. So this is how well something can go back to its original shape when it's been applied with force. So for instance, this spring here is given different weights. These look like little gorilla monkeys to me. But I believe they're supposed to be a chain, metal chains. The more weight that's applied, you can see if you were to put a straight line across here, it changes in length, right? It's not able to keep its original shape because it has to extend due to that force that's being applied. So as the load increases, so does the elongation. This image is also in your text as well. Here we have our original shape, and then we have compression forces, which would come down, and it almost constricts a material. And then we also have tension, which almost spreads it out, right? Sometimes compression of atomic bonds happens when objects are bent. And then we want to see the ability, can these atoms return to their original state? Next we have strain. So this is the change in length divided by the original length. So it's measured as a fraction or percentage. This is going to look familiar. We have this image again. So how it got that 10% or that 1.1 was 11 divided by 10. So this change final length was divided by its original length. So that's the amount of strain that was placed on this object. And then next we have stress. So that's the force that develops in a loaded object. It's proportional to the load, also related to size. So again, remember, stress is going to equal load divided by area, and that can either be in PSI or pascals. Okay, so an example here again, this is a little bit different than that other spring. You can see here this spring eventually gets wider. So these are different springs with weight added. And this spring is able to keep its original shape because this spring is actually longer lengthwise than this one, right? Because it's wider. So what's the big relationship between stress and strain? These things are always going to occur together. You're going to want to remember the modulus of elasticity is stress versus strain. It's characteristic of a material and its atomic bonds. And if it has a higher modulus of elasticity, it's a stronger, more stiff material. So the way you can think of this is that stress is the force that's experienced by an object that can change its shape. And then while strain is that change in shape when that stress is applied. So there are different parts of the stress-strain plot. There's an elastic deformation. This is when the stress is removed, and whatever that material is, it can go back to its original length. So think of that spring. Once you take that weight off that spring, it's able to go back to its original length, hopefully. Plastic or permanent deformation. This is, let's say that same spring, we keep putting weight and weight and weight on, and we leave it on there. Eventually, it's going to stay stretched out after that stress, or like a rubber band over time, it's going to get stretched out and be a different shape. Then we have the elastic limit, proportional limit, or yield point. So this is when something begins to deform. These are usually used interchangeably, but they are three different in measurement methods. And then ultimate strength, that's when something just finally gives out and it has to break. So let's look at that in a graph form. I think it makes more sense looking at it this way. So you have your stress applied, and it's going to affect the strain on that object, okay? So we have our slope, which is our modulus of elasticity. Eventually that stress is going to get to a point where it's going to change that object, change the shape. So that's our yield point, proportional limit, elastic limit. And eventually, if so much stress is applied, something could break. So a person that's a bruxer, let's say they have a composite class 1 filling on tooth number 2. They're just grinding away. Over time, with that stress of bruxism, that composite could eventually start to change its shape a little bit, and then eventually a fracture could happen. So hopefully that makes sense with that analogy, but I think visually seeing this, I'm more of a visual learner, so seeing that really helps me understand. And there are different types of stress. Not the type that you are experiencing in the dental hygiene program, but there are quite a few that can be applied to a dental material. We have compression, which is something pressing down. So for instance, with bruxism, the teeth are pushing down on a restoration. If the patient has restorations, the teeth are pushing and compressing that. Alternatively, there's tension. So if you remember that slide from before, I'll pull it up again here. So the person's bruxing, and let's say this is their amalgam filling, which is pretty resistant to these forces. But the person is bruxing, grinding, clenching. That's going to cause the surface of that amalgam to compress a bit. And then tension is going to mean where the bottom of that filling is going to kind of flex up a little bit. So that is more of, again, a pulling stress. Shear would be a sliding stress, so someone sliding their teeth side to side, back to front, that will kind of slide across the dental material. Torsion is a twisting stress, and then bending is pretty common, and it has different types of stresses. When something is bent, one side is compressed, and then the other is stretched or has tension. So that same image, again, that we saw, this is our bending force. Although something's happening on the surface, something else is happening below. And again, too, there are also a sliding stress that happens during bending too, actually. So let's look at different dental materials and how they would place on our stress strain plot. So you have your impression material, it's pretty soft, it's easily broken. you don't have to apply much stress for it to change shape, right? A gold crown is going to have significantly more resistance to strain before it starts to change its shape, and your ceramic crown is going to be highly, highly strong on the stress strain plot. It's going to take a lot to break that ceramic crown. Okay, and then we're going to talk a little bit more in depth about other mechanical properties. Poisson ratio, resilience and toughness, fracture toughness and fatigue, and then our time-dependent properties, which include creep and stress relaxation and stress concentration there. So Poisson ratio, what is that? You need to think about this as something being perpendicularly applied to the dental material. So this is a comparison of the strain in the direction of the stress that's going to be perpendicular. So, and the material is going to change in 3 dimensions. So this rubber band has 2 lines drawn on it. It's just sitting there rested. But then if you stretch it out, look how much the ink stretch out. The distance between those ink spots stretches out. So it's expanding. You can see how much thinner it is. So it's changing in its width, its length, and we can't really see the height of the rubber band, of course, but being stretched out, you know that it's going to be thinner. So, for instance, if you're biting on a filling occlusally, it's going to microscopically stretch wider in the mesial to distal and also buccal to lingual aspects. So it's perpendicular to the stress. It's not parallel. So you're biting down on occlusal filling, it's going to stretch out all those different ways below it. And then we have resilience and toughness. So resilience is a material that can absorb energy and keep its shape. So an example of this is a mouth guard that athletes will always usually wear during most sports. Toughness is a material's ability to absorb energy up to that failure point or that breaking point. An example is a helmet for football, helmet for bicycle riding. How tough can it be until it breaks, right? And then resilience and toughness can also be represented on our stress and strain plot. So remember, our yield point is where that material is going to start changing its shape from the amount of force and stress that it's applied. So that is its ability to keep its shape. Meaning the resilience. Once it begins to change, that includes all of its toughness to keep on going, even though its shape is changed until it completely breaks apart and fails. Okay? Fracture toughness. This is how a material can, or measuring that energy that it takes to break that material when there's a crack present. So these 2 images were really helpful. Sometimes around restorations, you can start to see fracture or craze lines begin happening here. This one has a really, really distinct fracture line that's right down the middle of the tooth. Things that have low fracture toughness would be things such as glass or dental porcelain. They're a little more prone to fracturing more easily compared to metals. And in these areas, it's actually the tooth structure. I don't want you to get too confused here, but there aren't fractures in the metal, right? They're in the tooth structure. So some of these metal areas put a lot of stress on the tooth area, especially if this person is a clencher or grinder there. But metals have a high resistance to fracturing, whereas other materials, dental porcelain, for example, have a low fracture. And then we have fatigue. So that is a material object failure due to being stressed repeatedly. For instance, this was an attempt for a root canal, and an endophile goes down in there to try to clean that out. It was used, but it broke off because it got so stressed that it just broke. This scaler here broke off, and this is just a side note. I've heard of some hygienists that have their instruments re-tipped. I've never done that. I don't know if that compromises the strength of the instrument, but it's kind of interesting that that's available. But in another great example too is bruxism. Clenching and grinding can do a lot of wear on dental materials, and eventually they'll get to a point where they can definitely fracture. Okay, almost towards the end, you guys. Then we have time-dependent properties. We have creep, which is a small change in shape when an object is under continuous compression. So this can happen to our amalgams and composites, fillings that are there because they are constantly in saliva, different temperature food, beverages, different hardness of foods, and over time they keep getting compressed, which can eventually change the shape. For instance, certain sealants, over time they can get worn down because the material is not as strong. And then you have stress relaxation, which is a slow decrease in force over time. So for instance, rubber bands get stretched out. If you think of even ortho rubber bands, they can only be used for so long, right, before they're no longer useful. And then we have stress concentration. So that's stress being placed in a specific area. And in turn, though, that can increase stress around defects because it's a weaker spot. So for instance, you want to make sure you avoid having bubbles in your sealants because those are defects that that force can go through those defects and voids really easily. And that increases the likelihood of a fracture. So there's an example here of cutting glass. You can see this etched glass. How they do that is there's a scratch made precisely where it's wanted, stress is applied, and then it can eventually get the shape that's desired. Although, now that that's happened, these areas are more fragile too. So a dental example of that would be with a tooth prep or anything like that. If there's anything wrong or a defect, of course it's not going to hold up. So all right, thank you so much, you guys, for listening. We do have one more chapter this week, chapter 5, which we'll go over next.